So in this video, we're going to talk about random variables. So often when we're performing an experiment, the sample space, we want to use the sample space so that it reflects the outcomes that we care about. But oftentimes we end up using a sample space that's chosen so that the probabilities are easier to compute. So we want a sample space that's uniform. Okay, so this is where random variables can help us. So let's just think about this example to illustrate this idea. So an experiment consists of flipping a coin, okay, 3 times. And we're recording just the number of heads. Okay, so not in what order they come, just the number of heads. So we don't care where they occur. So the sample space that we probably would like to use is going to have the outcomes, things that we might actually write down. That's the number of heads. So we could get 0 heads, 1 head, 2 head, or 3 heads. Okay, the problem with this sample space is that these outcomes are not equally likely. So this sample space is not uniform. Okay, so then our counting method to compute the probability goes out the window. So what we're going to use instead, or what we often use instead, is a sample space that gives us even more information. Okay, so for this one, because we're just going to write we're going to think about the order that the heads and tails occur. So we're going to have 8 possible outcomes here. I guess I made this first one too big. Okay. So we instead use this sample space, which is uniform. Okay, each of these outcomes has the same probability of occurring. So then, if we wanted to compute the probability of flipping exactly 2 heads, okay, this is what we did before. Now we can use the uniform sample space to say this is the number with exactly 2 heads divided by the number in the sample space. So these 3 here look like they have exactly 2 heads. So I'm going to end up with 3 over the 8 that are present. Okay, so this is what we did in chapter 2. Okay, so it's the same idea, nothing's new. But here, we're more interested in the numerical value that's associated with each outcome, rather than the order that they happened. So this is the idea behind a random variable. So a random variable is a function that assigns a numerical value to each event, so for each outcome in the sample space. So for our random variable, I'm going to call it x. It would be the number of heads flipped. Okay, so what you think of is tagging each outcome. Okay, so this heads would be tagged with the number 3. All of these ones in yellow would be tagged with the number 2. Down here, I have 3 number 1s. Okay, and then I have 0. One outcome that will get tagged with a 0. Okay, so that's the idea behind a random variable. So with that in mind, basically we just are changing the notation. It's a bit easier to write these events. So here I defined the random variable x to send each outcome in S to the numerical value representing the number of heads. Okay, so that's what I wrote up above. Okay, and I tagged each of these outcomes in our uniform sample space. And now we can better write, okay, so now the probability of exactly 2 heads, so what I wrote before, so I described my event, I can describe it more succinctly as writing probability, the random variable x, random variable x equals 2. So what this means is that the outcome that occurs in our experiment is one that would be tagged with the number 2. Okay, those are exactly the highlighted ones, so this is the same probability. We already computed it. It's 3 over 8. Okay, so you can see this is the same. Okay, so these two events are talking about the same thing, just different notation. Okay, and this random variable notation actually lets us write a variety of different events using only just the same notation. So a note, when we're talking about random variables, we normally use, oh, here it is, some notation. So we normally use capital letters for the random variable. And then we use lowercase letters to talk about the numerical values that could occur. Okay, so it's usually x and y. And then we would say p of x, so little p of x, this is just us being lazy. So this is the same as the probability that our random variable outputs little x. So same idea here. Okay, so outcome that occurs is tagged little x, okay, by the random variable capital X. Okay, so another way to write this is the probability capital X equals little x. Okay, but you could just write p of x, the little x. Okay, so then that means all the same thing. So we also have this idea of a probability distribution table for random variables. So it's the same as what we had in chapter 2. So it's a table that lists each possible output of x. Okay, so in comparison, it was all the outcomes of the experiment in chapter 2. So here it's all the outputs of x together with their probabilities. Okay, so if we do it for the example previous, okay, so our possible outputs, so those are our possible little x's. Okay, these are how many heads we could have. Okay, so we could have 0 heads, 1 head, 2 heads, or 3 heads. Okay, that's all we could have. And then down here, we're going to have their probabilities. Okay, so we already did the one with 2 heads, we said was 3 over 8. Okay, now if we go back to our sample space, we'll see that there's also 3 with number 1. Okay, there's 1 with number 3. And there's 1 with number 0. Okay, so what we're going to have is the 0 and the 3 are both 1 out of 8. Okay, and the number 1 is also 3 out of 8, like the number 2. So notice here that these probabilities sum to 1. Okay, that's the same. So all these probabilities would add to 1, just like before. Okay, so all these things are the same as before. So some important notes. So if capital X has possible outputs x1, x2 to xn, then each of these p of x's, okay, so p of, say, xi for any I, these are probabilities. So they have to be between 0 and 1. Okay, that's our rule for all probabilities. So it applies here. And also, if we add them all up, so p of x1 plus p of x2, okay, all the way until p of xn, we should sum to 1. Okay, so this just says that these probabilities in our table sum to 1, which is again the same as what we had in chapter 2. So to take this a bit further, so same example, what would we expect to happen? Okay, so this word here is important. What would we expect to happen if we performed this experiment 8 times? Okay, so what I mean by that is we flip a coin 3 times, record the number of heads, and then we do that process 8 times. Okay, now the reason I picked 8 here is I'm hoping to convince you, okay, because the sample space has 8 things, okay, that these probabilities are sort of the chances of getting each thing. So in a perfect world, if we did this 8 times, we would get 0 heads. Maybe I'll make it so you can still see this. So we would expect to get 0 heads 1 time. Okay, and we would expect to get 1 head 3 times because the probability is 3 out of 8. And we would expect to get 2 heads also 3 times. Okay, and 3 heads 1 time. Because of their probabilities. So again, this is a perfect world. This doesn't happen all the time. Okay, but this is what we might expect to happen given the probabilities. So, how many heads would we expect to get on average? So if you perform this 8-step experiment many times, so now we're ramping it up. We're doing this 8-step experiment over and over and over. Okay, we want to get an average. Okay, so we want to average these numbers. So how do we do an average? Well, we add up all the numbers and divide by how many there are. So I have 0 once, I have 1 3 times, 2 3 times, and 3 once. Okay, and divide by 8. Now if you compute this, you're going to get 1.5. Okay, I don't actually care what the number is. What I want to do is rewrite this. So here I have 1 0 plus 3 1s plus 3 2s and plus 1 3. And because I have a fraction all over 8, I can put each one of them over 8. Okay, so that's like a common denominator. I'm just doing that backwards. So then I'm going to rewrite this. So instead of doing the multiplying on the top first and then dividing, I'm going to do the 1 over 8 first. So divide and then multiply by 0. Okay, so then I have 1 times 3 over 8, 2 times 3 over 8, and 3 times 1 over 8. And now look, we have the output with its probability, the output with its probability, the output with its probability. So this is the idea behind computing an average. Okay, so this is 0 times p of 0 plus 1 times p of 1 plus 2 times p of 2 plus 3 times p of 3. Okay, so this is how we compute an expected value. Okay, so this, I'm just trying to sort of convince you why we might do what we do. Okay, so hopefully this was convincing enough. So more formally, given this probability distribution table for a random variable x, okay, so we have outputs or outcomes xi, okay, so these are all the possible outputs of x together with their probabilities. Now again, we've even made it more lazy. So they're saying pi in place of p of xi. Okay, so then we define the expected value of x. Okay, so we call it capital E of x. Okay, to be x1 times p1 plus x2 times p2 plus to xn times pn. So what you do is you multiply each output by its probability. Okay, so you multiply like vertically, okay, and then you add each of them. And this gives you the expected value of x. Now, an important note, okay, the expected value is an average of what occurs in a large number of experiments. Okay, so if you were doing it over and over and over. So because it's an average, it does not need to equal a value on a single experiment. Okay, so the expected value, so e of x, does not need to be one of the xi's. Okay, you don't need that. It's an average, so it could even not really make sense. So like, for example, up here, I said it was 1.5. There's no way to get 1.5 heads, right? Remember, the x is the number of heads, right? So each of our outputs is an integer, okay? It's fine that the expected value is a decimal, like has a decimal. So because it's an average. So it doesn't have to be one of the actual outputs. So let's just do one more example. So suppose Tom convinces Dina to play a game. Dina pays $3 to play. Okay, so she pays the $3 no matter what. And she gets to pick one card from a standard deck. Tom tells her that he's going to give her $5 if she draws a face card. So that's Jack, Queen, or King. And $10 if she gets an ace. But if she gets anything else, he just keeps her $3. So we're going to define the random variable to be Dina's, okay, so net winnings. So I just want to emphasize, what does net winnings mean? It means your winnings minus your cost to play. Okay, so minus the cost. That's when we say net. So let's first make the probability distribution table. So I want all the possible outputs of our random variable, okay, together with their probabilities. So what could happen? Sometimes it helps to write what she actually picks. Okay, so she might pick an ace. Okay, that's one category. Now this is not an output, it's just helping us arrive at the output. So if she picks an ace, what's going to happen? Well, Tom told her he'd give her $10, but she already paid $3. Okay, so her winnings are $10, but the cost is $3. So the output is going to be $7. Okay, now she might pick a face card. In that case, Tom told her that he would give her $5. But again, remember, she paid $3. So her net winnings are going to be $2. Okay, now if she picks anything else, she doesn't win anything, but she paid $3. So the x value is going to be minus 3. Okay, she loses $3 here. So now we want to compute the probabilities. So she's only picking one card. Okay, so one card from the deck. So these probabilities are fairly straightforward. So there's 4 aces. So there's 4 aces out of 52 cards. So the chances that she picks an ace is 4 out of 52. There's 12 face cards, so 4 of each of Jack, Queen, and King. Okay, so 12 face cards over the 52 total cards. And that leaves 36 other cards over the 52. Okay, so that would be our probability distribution table. And now we want to know, how much should Dina expect to win? Okay, so that means we want to compute the expected value. Okay, so we're computing E of x. So because we have the probability distribution table, what we want to do is take each output and times it by its probability. So I'm going to do 7 times 4 over 52 plus 2 times 12 over 52 plus negative 3 times 36 over 52. Okay, now if you compute this, you should get negative 1.08. So what does that mean? If Dina plays this game with Tom many times, okay, on average, she should expect, because this is minus, her winnings are negative, so she should expect to lose $1.08. On average, each round. Okay, if she played a lot of rounds. Now notice that this is not one of the outputs. Okay, that's fine. It's an average. So because the probability of her losing $3 is much higher than the probability she wins, she ends up losing on average. So she's going to lose more than she wins. And even though she's winning more money, it doesn't matter. So does this seem fair? Well, maybe if you're Tom, you might think so. Okay, but not if you're Dina. So we call this not fair. Okay, so a fair game. In a fair game, no one has an advantage. So here, Tom is expecting to win more often. So, by the way, maybe I'll write Dina expects to lose $1.08. Another way to interpret this is Tom expects to gain. $1.08 on average. So if Dina's losing, that means Tom is gaining. So the way we define a game to be fair is that it's a game where the expected value of your random variable, so